Statistical Mechanics. I'm John Preskill. The course has a website, different than last term. It's www.theory.caltech.edu. Tilda Preskill, my last name, PH12C. The administrative details are similar to last term, and they're all on the website. That's where the homework will be posted. We have a textbook. It's Thermal Physics. Second edition by Cattell and Cromer. I think it's a good book. I'll be following it fairly closely. We intend to cover chapters 1 through 10, parts of chapter 14, and some extra material that goes beyond the book. I'm going to have my sloppy handwritten lecture notes, they're already there actually, posted on the web. And I guess maybe there's going to be video available. So you got the notes, maybe you have the video. So why come to class? I mean, I'd like you to think of it as the difference, at least as far as the notes go, between reading Shakespeare and seeing a live performance, you know. And if you don't think the performance is up to snuff, then of course you know what your options are. But I really think coming to class helps you learn the stuff, but of course that's up to you to decide. This is Caltech after all. Now, thermal physics has two main components: thermodynamics and statistical mechanics. What's thermodynamics? Well, we can kind of characterize it by the main concepts it deals with. Concepts you're familiar with mostly, like energy and work and heat and temperature, and most centrally of all, entropy. It has a very clean formulation. We can kind of boil down the essence of thermodynamics to some fundamental principles which can be stated. As 3 or 4 fundamental laws. And that gives the subject a kind of pristine beauty. There are many applications. That won't be our main focus in the class, which is really to emphasize the foundations. But if you need motivation for studying the subject, there are a huge number of applications to science, technology, and actually even beyond. I'll just say many for now. The math is pretty simple. The math for thermodynamics is mostly differential calculus, and in particular the calculus of functions of several variables. So many of the mathematical manipulations involve partial derivatives and total derivatives of functions of several variables. And the key to the subject, really, what we want to gain a deep appreciation of in the course, is the concept of irreversibility. The idea that Sometimes systems evolve forward in time in a certain way, so that if you see a movie of the system evolving backward in time, it makes you laugh because it's so silly. That's irreversibility. A guy can jump off a diving board into a swimming pool, and the potential energy released in his fall gets dissipated into the molecular motion of the water. And so that's not so funny, but when you run it backwards, all the molecules push the guy up into the air and onto the diving board, and everybody laughs. That's irreversibility. And really, coming back briefly to the applications, the foundations of the subject are really in technology, and the importance of irreversibility as a limitation on technology. The subject was born in the 19th century in efforts to understand things like heat engines, and the applications are to things like refrigeration, as well as many more esoteric scientific applications, understanding phases of matter, and so on, which we'll discuss in detail. The other main topic, Stat Mech, short for Statistical Mechanics. And you can look at statistical mechanics as an attempt to find the deeper principles, a successful attempt, to find the deeper principles underlying thermodynamics, which explain thermodynamics. The central achievement of statistical mechanics is to explain thermodynamics on the basis of microscopic laws governing the microscopic structure of matter. So, explain foundations of thermodynamics from microscopic laws. And what's the key to the subject? The key is probability theory. Applied to systems with many degrees of freedom, like systems of many particles. A gas with an Avogadro's number of molecules in a box. Applied to systems in which something is large. To be concrete, I'll say with a very large number of particles, like 10 to the 23 or so, of the order of Avogadro's number. The idea is that we can use probability theory. We can compute average properties of systems, averaged over many microscopic states, and the deviations from that average behavior are rare and small, or at least large deviations are rare. Typical deviations are very small. So the average behavior is a very good predictor of how the system will behave, and that's what we can compute. So what we do is we predict average behavior and observe, or mathematically show, that big fluctuations, that is, big deviations from average behavior, are rare. And for systems with many, many particles, actually very rare, so they essentially never happen. And the average behavior really tells us what's going on. That's the idea. Now notice that here, probability enters in a rather different way than in the study of quantum mechanics, what you learned in Physics 12b. In quantum systems, probability is intrinsic. Even when you have the most complete possible description of a system, you're unable to predict, except by assigning probabilities, the outcome of measurement. Okay? You couldn't possibly know more about the system. You still can't predict what will happen when you measure it. That's not what we're talking about here. What we're talking about is that probability arises in practice because we don't have a complete description of the system. There are many possible microscopic states. We don't know which one. But we don't need to know which one because all these microscopic states that occur with reasonable likelihood lead to similar behavior. So I'll just say, unlike quantum mechanics, as in physics 12b, this is probability arises in practice because we don't have complete knowledge of the system's actual state. Not in principle, as in the quantum measurement process. What's the math? Well, it's probability theory. And really, it's counting. Counting the number of states that a system can be in subject to constraint. Sounds simple, but it's not always simple. Sometimes counting is hard. Conceptually, it's simple. In practice, it can be hard. Now, of these two pillars of thermal physics, statistical mechanics and thermodynamics, which are, of course, closely related, as I've already emphasized, in Physics 12c, our emphasis will be on statistical mechanics. We'll talk about thermodynamics. We'll see how it emerges from the statistical mechanical picture of the world, but our main goal will be to understand the foundations and applications of statistical mechanics. And it's really a great subject for Physics 12 because from a few fairly clear, conceptually, and accessible principles and methods, we can understand a lot of physics, and that's what we'll try to do in this course. Now, statistical mechanics the focus of Physics 12c is also an extremely active subject of contemporary physics. Much of what physicists call the study of condensed matter, which means solid-state systems and systems of many particles in various settings. Much of those studies are based on applications of statistical mechanics to things like the different types of phases and phase transitions. One of the things we'll be talking about, transitions between phases, to different classes of materials, and various ways of classifying the properties of systems with many particles. Okay, so let's start counting. Any questions about all this so far? So let's start to familiarize ourselves with the main idea that we're going to use throughout the course. It's a simple idea. We have some system. Maybe it's a gas. The important thing is it has many degrees of freedom. Let's say many molecules in a box. That's my picture of gas in a box. We specify some macroscopic property of the system that we can imagine measuring or characterizing the system, like, for example, the total energy. Now specify a macroscopic property like the total energy. Well, we don't specify it exactly to an infinite number of digits of precision, but to some approximation. So we say E is a lower bound on the total energy, let's say, and E plus delta E has an upper bound. The energy is in between. It's in that range somewhere. Okay, that's what I mean by specifying a macroscopic quantity. And of all the states that have energy in this range, well, there are many of them. Lots and lots of microscopic states. Lots of ways in which that energy could be shared as kinetic energy among the different molecules in the box. And now, for trying to understand what's going on in the box, we're going to rely on an assumption, which I'm not really going to justify from first principles, because doing so is actually not easy. So let's be honest and state it as an assumption, which is all microscopic states which are consistent with, I'll call it our macroscopic specification. I don't know, that's kind of an awkward way of saying it, but I've already said it. In this case, our statement that the total energy is in a certain range, all microscopic states are equally likely. It's a very egalitarian democratic principle. All the microscopic states have an equal right to be the microscopic state of the system, as long as they're consistent with whatever it is we know or we specify, like, for example, the total energy. So that means each one of those states, we're saying we're pleading ignorance. We don't know anything about the microscopic state, so we might as well assume that there's a uniform probability distribution in all the states. Each one of them, by a microscopic state, I mean, say, specifying the position and velocity of all the molecules in the box. Can't really do that in quantum mechanics. We'll come back to that. But anyway, some way of completely characterizing the state. And the probability of a state, in other words, is given by a uniform distribution for every state. It's just 1 over the total number of states. And actually, quantum mechanics helps us here. It helps us by allowing us to count states. States are discrete in quantum mechanics. At least if we have a system which has a finite volume, a finite size, then there's some Hamiltonian, say, which characterizes the state, and it has a spectrum of eigenvalues, right? You learned all about that in 12b. All the stationary states, there are actually a finite number of them in an energy range. In principle, you can count them all. In classical mechanics, it's a little harder to say, although you can do it, exactly what you mean by counting states, because they're really a continuum of states. In quantum mechanics, states are really discrete, which makes it easier to give a rigorous version of what we mean by counting states. In quantum mechanics, states really are discrete. And so can be counted. At least if we don't have an infinite system. In practice, we never do. And so, I've already told you what we're going to do. We're going to compute average behavior. So our job, as I've already said, but it's worth saying again, is twofold. Compute average behavior. For this ensemble. Of possible microscopic states. And verify that large fluctuations away from the average behavior are very rare. So the typical behavior of the system really is like we would predict by considering average behavior, averaged over this uniform ensemble. Well, you probably know what I mean by the fluctuations being small with large fluctuations being rare. But let's discuss that to remind ourselves what it means. So let's start with about the simplest example we can think of, which is we have a fair coin. Okay? Flip it. It comes up heads with probability 1/2 and tails with probability 1/2. So if we plot probability as a function of the number of heads that come up, the number of heads can be either 0 or 1. It's a flat distribution. Both heads and tails have probability 1/2. Probability 1/2 for 0 heads, if I flip it once. Probability 1/2 for 1 heads. That's for one coin. But I'm interested in what happens when I flip a lot of coins. Well, let's start with 2, just so we understand what we're doing. If I have 2 coins, each one comes up heads or tails, there are 4. I jumped ahead to 3 coins. There are 4 possibilities for what can happen. We can get tails twice, tails and then heads and then tails, or heads twice. So here we get no heads. These are the 2 ways of getting 1 heads, and there's 1 way of getting 2 heads. So if I divide by 4 so I get a normalized probability, the probability as a function of the number of heads looks like this. Oh, sorry, I jumped ahead again. So far, just 2 coins. We can have either 0, 1, or 2, with probability 1/4 of having 0 or 2, and probability 1/2 of getting 2 heads. And we can keep going, right? If I consider 3 coins, there are 8 possible outcomes when I flip a coin 3 times. If it's a fair coin, then there are actually 3 ways of getting 1 heads, 3 ways of getting 2 heads, 1 way of getting 3 heads, 1 way of getting 0 heads. The probability distribution looks like this, where these probabilities are 1/8 and these are 3/8. All right? So now I'm going to imagine I flip n coins, and n is a large number. 1, 2, 3, many. Well, now there are lots of possible outcomes. Flip a coin n times, there are 2 to the n possibilities. Well, you know that on average, the number of times I'm going to get a heads is half of the time. Now, the most likely possibility for the number of heads is actually n over 2. And around n over 2, there's a distribution, and it looks kind of like that. And in fact, in a sense which we'll make precise, this distribution becomes very narrow. As n gets large. It has a characteristic shape, which we call a Gaussian, or a normal distribution. And actually, this is a special case of a rather general result called the central limit theorem. The central limit theorem actually says this. Consider any probability distribution. This has some nice mathematical properties, but let's assume that it does. So let t be some variable. It was 0 and 1 in the case where I flipped a single coin. And I assign a probability to each value of t. And so there's some distribution. Here it is. Okay. It has some crazy shape, maybe. But now we sample from this distribution many times. So that means, weighted by the probability, I choose some particular value of t each time I take a sample. And I do that n times. And then let's consider the sum over those n samples of the value of t in each sample. I'll call that capital T sub n because I sampled n times. The sum of the result when I sample the first time plus the second time up to the nth time. And then I ask, what's the distribution for the sum? So in fact, when n gets large, the probability distribution for t sub n approaches a Gaussian, a narrow Gaussian like the one for the coins, when n is large. And that's what I mean by the central limit theorem. I'm not going to give a proof of the central limit theorem, but let's look at how it applies in more detail to the case of flipping a fair coin n times. Except I just remembered something. This is a physics class. Okay? So I'm going to make it sound like physics by saying, instead of flipping coins, I have a model of a magnet. So there's a big hunk of magnetic material. And in that material, there are a lot of spins. Maybe they're electron spins. I guess you know electrons have spin. And let's say each one of those spins can point either up or down along the vertical axis. Okay? Now, there's a spin at each of n sites in our magnetic material. Each is either spin up or spin down. And let's suppose that there's no particular reason for a spin to prefer to point up or down. So it decides at random whether to point up or down. For each spin independently, it has probability 1/2 of pointing up and probability 1/2 for pointing down. Well, it's a lot like the coins, right? They're like coins which I flipped, which are either heads or tails. Now, each one of those spins actually has a magnetic moment. And what we call the magnetization in our magnet is the sum with a sign, the difference between the magnetization due to all the spins which are up and the magnetization due to all the spins that are down. The magnetization I'll call it capital M, is the number of up spins minus the number of down spins times the magnetic moment of a single spin. So the magnetization is just the magnetic moment of the whole sample. If half the spins were up and half the spins were down, their magnetic moments would cancel out. But there might just by chance be an excess of either up over down or down over up. And as a result, there will be some non-zero magnetization for my bulk magnetic material, some big hunk of magnet with Avogadro's number of spins in it. So suppose the magnetization in this case is the macroscopic quantity that we're going to fix. And somebody can come along and measure it, okay, with a magnetometer. So that's the macroscopic quantity, which we specify. And we'd like to kind of understand from first principles what to expect when we measure the magnetization, okay? At least what's predicted by this model. So actually I can write the magnetization. It's convenient to write it as something I'll call 2s times the magnetic moment. This is, just to give it a name, I'll call it the spin excess. So in other words, I can write the number of up spins as half of the spins plus s, and the number of down spins is half of the spins minus s. The sum is n, and the difference between the number up and the number down is 2s. Let me call a number g the multiplicity of that particular value of the magnetization. It means the number of possible states of our magnet, where in a state I specify for every one of the n spins, whether it's up or down. This multiplicity is the number of states with spin excess to s, a specified value of s, and n spins total. And I'd like to compute what that is. So it's just the same mathematical question as asking how many ways, when I flip a coin n times, are there to get a number of heads, which is half of all the flips plus s. Same thing. But I made it sound like physics. Okay, so really we just have to find binomial coefficients. We think of Each time we look at a spin, it can be either up or down. There are n spins. So we can think of 2 to the n possible sequences, binary sequences, if you think of up and down as 0 and 1. Each sequence specifies which spins are up and which spins are down. I want to count all the sequences which have a specified spin excess. So there are altogether 2 to the n states. Each one is either up or down out of n. And how many of them have a specified spin excess? And what I mean by the multiplicity is the number of terms, the number of sequences, call it sequences, with a specified number of up spins, as I already said, 1/2 n plus s, and the rest down, which means there are 1/2 n minus s, which are down. And that's just equal to the number of ways of choosing and up spins out of altogether n spins, right? Which I can write as n factorial divided by the number up factorial divided by the number down factorial. That's because n factorial is the number of ways I can permute all the bits in the sequence. But n up factorial of those permutations just mix up the up spins with one another, and that doesn't change the state, doesn't change the configuration. So I divide by that. And down factorial of the permutations of all the down spins doesn't change the configuration because it just permutes down spins with one another, right? So let's just write out what it is. N factorial divided by n over 2 plus s factorial n over 2 minus s factorial. We want to understand how that quantity behaves as s varies. And to do that, we're going to make an approximation. Because we'd like to see this sharp Gaussian emerging from this description. I'm going to suppose that s is small compared to n. Well, actually, we'll be able to justify that in retrospect when we see what the answer is. It's just saying that the very large fluctuations are extremely rare, so forget about them. We're only going to have to study the small fluctuations in which the spin excess is small compared to the total number of spins. And we'll make another approximation in evaluating n factorial, the Stirling approximation. N factorial can be written as 2 pi n to the 1/2 power, n to the power n, e to the minus n, plus some stuff in the exponential that becomes unimportant when n is large. I can expand that exponential, but we're going to ignore all these corrections. That means we'll have the right answer up to some factor, which is the exponential of this number, which is very close to 0, up to some factor, which is very close to 1. Okay? And if you haven't seen the derivation of the Stirling approximation, it's in Appendix A of the book. It's very easy to understand the n to the n, e to the minus n. You have to work a little harder to get the 2 pi n to the 1/2, which actually isn't all that important anyway. But to understand the terms that are important, just note, consider taking the log of n factorial. The log of n factorial, well, let's say the natural log of n factorial, the natural log of the product from m equals 1 to n, because that's what a factorial is, of m. Taking the log of the product becomes the sum of the logs. And when n is very large, we can approximate the sum by an integral fairly well up to some additive factor which is of order 1. So it's like integrating 1 to m dm log m. And you know how to do that integral. It's m log m minus m, evaluated at n and 1. The contribution from the lower limit of integration isn't too important. So it's essentially n log n minus n. And what I have here in n to the n e to the minus n is the exponential of that. And like I said, with a little more work, you can get the 2 pi n to the 1/2. Okay, so let's just plug in to the Stirling approximation the factorials that we want to evaluate here. Maybe it'll be helpful to write this as n factorial divided by, let's factor out an n over 2, times 1 plus 2s over n factorial, and n over 2, 1 minus 2s over n factorial, and apply Stirling's approximation to that. So for the n factorial in the numerator, I have 2 pi n to the 1/2, n to the n, e to the minus n. And then, for the first factor in the denominator, because it's in the denominator, I turn everything upside down, so it becomes 2 pi times 1/2 n, 1 plus 2s over n to the minus 1/2, and then n over 2, 1 plus 2s over n, raised to the power, because it's in the denominator, minus n over 2, 1 plus 2s over n. And then for the other factor in the denominator, 2 pi, 1/2 n, 1 minus 2s over n to the minus 1/2, n over 2, 1 minus 2s over n, raised to the power, because it's in the denominator, minus n over 2 times 1 minus 2s over n, except I guess I also forgot the exponential, which here would be e to the n over 2 times 1 plus 2s over n, and here would be e to the n over 2, because it's in the denominator, 1 minus 2s over n. Now we need to multiply together all these factors. That's not in the exponent. It looked like it was, so I'll rewrite it. E to the n over 2, 1 minus 2s over n. Well, when I multiply this exponential times this one, this annoying 2s over n goes away, and then I have an e to the n, but that cancels the e to the minus n, so I can get rid of all that junk. And then I have an n to the n, and here I have an n to the minus n over 2 times 1 plus 2s over n, and here an n to the minus n over 2, 1 minus 2s over n. And so that all cancels too. Okay, so I can get rid of that, and that, and that. And then I guess I should combine together the 2 pi's and stuff. So I had a 2 pi in the numerator, but I had two pi's in the denominator, all to the 1/2 power. So it's 2 pi to the minus 1/2. And then, well, there's this 1/2 raised to the minus 1/2, and then another 1/2 raised to the minus 1/2. So altogether, that's a 2. And an n to the 1/2 and 2 n to the minus 1/2. So that gives me an n to the minus 1/2. Now we got this 1/2 here, and it gets raised to this power. So I have 1/2 raised to that power times 1/2 raised to that power, and that gets rid of those 2s over n corrections. So that just gives me a 2 to the n. And then let's look at what we have left. We've just got the 1 plus 2s over n to a power, the 1 minus 2s over n to a power. We also have the product of these 2 factors. But that's not important, actually. But I do want to keep track of the 1 plus 2s over n to the power minus n over 2, 1 plus 2s over n, and then 1 minus 2s over n to the power minus n over 2, 1 minus 2s over n, and that last factor, which I'm actually not going to worry about, which is this 1 plus 2s over n times this 1 minus 2s over n, which is altogether 1 minus 4s squared over n squared to the minus 1/2. But I'm just going to approximate that by 1, because remember, we're going to assume that s is small. Okay, so the only thing we have to work on a little bit more is this product of factors. At this point, it's handy to take the logarithm, and then after we get the result, we can exponentiate it. So what I'm taking the logarithm of is this times this. And so I have minus n over 2, 1 plus 2s over n, times the log of 1 plus 2s over n, from the first factor when I take its log. And then I get the same thing, but with s replaced by minus s. And now remember, we're going to suppose that s is small compared to n, and that means we can expand the logarithm in a power series and just keep the leading terms. If I write the log of 1 plus x, I can write that as x minus 1/2 x squared plus higher order in x, which I'm going to safely be able to ignore. And so this becomes, if I make that expansion, minus n over 2, 1 plus 2s over n, and then 2s over n minus, because of the 1/2, 2 s squared over n squared. And let's remember, we still have the plus the term with s goes to minus s. Now, any term that's linear in s, that's going to go away, because we're going to combine together the term with a plus sign and the term with a minus sign. So the linear terms are going to cancel out. Yeah. Linear and s cancel. Well, we want the quadratic terms, and they come from 2 places. from the 1 times the minus 2s squared over n squared, and from the 4s over n times the 4s over n. 2s over n times 2s over n, which is 4s squared over n squared. Then we also have the minus n over 2. So it's actually minus n over 2 times 2s squared over n squared, plus the higher order stuff in s that we're going to be able to ignore. But then we get the same quadratic term, because changing s to minus s doesn't change the quadratic term, from the other term, so we multiply it by 2. Okay? And so for the quadratic terms, when we combine the factors together, the 2 cancels the 1/2 here. I have minus n and an n squared here, so it's minus 2s squared over n. Okay, we did it. So now we have our expression for the multiplicity, which is a good approximation when n is large, needed to justify the Stirling approximation, and when s is small compared to n, needed to justify our power series expansion. Let's put it all together. So, the number of states with the specified multiplicity, with the specified spin excess, the multiplicity for the specified spin excess, well, we have that prefactor that we worked out over there. We put the factors together. I have a 2 over pi n to the 1/2, and I have a 2 to the n. And this was the logarithm of the rest of it, so now let's take the exponential. And I have the exponential of minus 2s squared over n plus higher order in s over n, which I'm neglecting. Okay? This is the Gaussian. So if you plot it as a function of s, the excess of heads over tails, or spin up over spin down, it's a Gaussian centered at the origin, at s equals 0, symmetric about s equals 0. Is it narrow? Well, how wide is it? We can ask, how far does s have to deviate from the most probable value in order for the function to drop to 1 over e of its peak value? Well, it does so when the argument of the exponential is minus 1, or 2s squared over n equals 1, which means that the absolute value of s could be either positive or negative, is 1 over the square root of 2 times the square root of n. So it's actually wide when n is large. Its width grows as n grows. But if I compare that typical deviation of s from the most probable value of 0 with the full range of s, which is of order n, if I compare s, where the function is down by 1 over e from its peak, to the value of n, that's small. So I haven't used this one yet. In other words, the absolute value of s divided by n is 1 over the square root of 2n, and that goes to 0. as n goes to infinity. So that's what I mean by narrow for n large. It means, in other words, if I have 10 to the 22 spins in some macroscopic hunk of magnetic material, the typical fractional deviation from half spins up and half spins down is something like 10 to the minus 11. It's really small. That's what I mean by narrow. And this, in this particular example, illustrates the main idea, which is fluctuations from the mean are rare. We have a big magnet, lots of spins. They decide at random to be up or down. Then the up spins nearly cancel the down spins. But there are fluctuations. But the fluctuations are a small fraction of all the spins. For all practical purposes, if I measure the magnetization, if I compare the magnetization for this material in which the spins decide at random whether to be up or down to a polarized material where all the spins point in the same direction, if there are 10 to the 22 spins, the magnetization is smaller by a factor of 10 to the minus 11 than the fully polarized material. Very hard to measure magnetic moment to that accuracy. It's effectively zero. And that's the basic idea of statistical physics in action. So let's just say it a little bit more generally. Question?
Yeah, throughout this we've assumed that the electrons are all distinguishable, right?
Well, that's right. I'm considering the spins to be distinguishable for this discussion. I didn't actually say they were. Well, I did say they were electrons. You got me. Okay. But
so is that going to be true in everything we do?
No. We will, in fact, study in great detail the consequences of indistinguishable particle statistics later in the course, because it's very important for understanding a lot of physical phenomena to know that both electrons and other types of particles like photons are really indistinguishable. We'll get the counting wrong if we don't take that into account. In this case, though, what I can justify what I'm doing, even if they are electron spins, because although I can't really say which electron is which, it is possible for an experimentalist, it's actually something that experimentalists have just recently learned to do in practice, it's possible to go in and measure the spins one at a time and verify whether they're up or down. So this really has a physical meaning to say that there's a configuration where each spin is either definitely up or down. So we can do the counting this way, even if they're electrons. If I tried to put labels on the electrons, I would never really know who's who, but I do know in each position whether the spin is up or down. All right, thank you. Good question. So let's say this in a somewhat more general way. Consider any old random variable. A random variable is just something which can take any value in some range of values, each of which we can assign some counting factor to. So we can say that a particular value of the random variable gets higher weight because it corresponds to more configurations. So for any random variable, consider making some count or histogram of number of configurations for different values of S. Here's a histogram. I'll call it Q of S. So this counts a number of configurations corresponding to specified value of S So that's what we've discussed in detail for the case of spins which are either up or down, where the configurations are states in which each spin is specified to be either up or down. But let's take a more general point of view. There are lots of states. There's some variable s. And for each value of s, I can count all the states which give rise to that value. And therefore, I can speak of a probability for each value of s if we use our assumption that all the configurations are equally likely, that we have a uniform distribution on the microscopic states. So if all configurations are considered to be equally likely, which we assume to be the case, then I can speak of the probability of our random variable taking the value s. I just have to take q of s, which counts the configurations for which the random variable has that value, by a normalization factor, which is the sum over all values of q of s prime. So with that normalization, the probability, as it should, obeys the rule that when I sum over all values of s, the probability of s is equal to 1. The probabilities sum up to unity. Now, when I speak of average values, if I'd like to know in this ensemble what we predict for the value of s, I consider the mean value, I'll denote it that way, governed by this probability distribution, and that just means the sum over all values of s times the probability of s. And indeed, for any function of s, I can compute its mean value as well, and that's our prediction up to small fluctuations for the value of that function in this system. It's just the sum over all values of s, the value of the function for that value of s, times the corresponding probability of s. Now, in the case of our binomial distribution that we've been describing for our model of a magnet, when we sum up the multiplicity for fixed n and all possible values of the excess s, we get 2 to the n, because that's the total number of configurations for n spins, each of which can be either up or down. The total number of outcomes if we flip a coin n times. So we should normalize to get a probability distribution from our multiplicity function. And we do so by dividing by 2 to the n. Now, let's write down what it is. We have our expression for the multiplicity. Here it is. Conveniently, it has a 2 to the n in front. So now we divide that out, and we can interpret the result as a probability for the spin excess to take a specified value. And it's given by this Gaussian function. Now, if we want to use that probability distribution to compute expectation values of things, convenient to notice that as we sum over S, which advances by value 1 as we change the configuration, when S changes to S plus 1, the exponential changes very little because of the n in the argument of the exponential in the denominator. So when we sum over values of S, that can be very well approximated by an integral. So in fact, what I called the excess can range from minus n to n. 2s can go from minus n to n. And we can imagine integrating ds instead, thinking of s as a continuous variable, and get a very good approximation for the purpose of computing our expectation values. Furthermore, we can extend this integral over the whole real line. Although 2s is never really smaller than minus n or larger than n, the exponential is incredibly small when we get to those endpoints of our summation, going like e to the minus n, where n is 10 to the 22 or something. So we make an entirely negligible error if we extend our integral to minus infinity to infinity. So because distribution has a very small tail at large absolute value of s, can extend integral. And you can imagine integrating s from minus infinity to infinity. So let's just, as a sanity check, because we should always check ourselves, because sometimes mistakes get made, verify that our distribution really is normalized correctly by evaluating this integral. Check normalization. We want to verify that when we integrate our probability distribution, ds from minus infinity to infinity, we get 1. So the integral we need to do is the integral of 2 over pi n to the 1/2 times e to the minus 2s squared over n, because that's what p is. Here it is. So why don't we change variables and write x as the square root of 2 over n times s, or in other words, the ds becomes the square root of n over 2 times dx. The argument of the exponential becomes e to the minus x squared. So now I'm integrating dx. I have the square root of n over 2, and I have the 2 over pi n to the 1/2, and e to the minus x squared. So that's actually, because the n's cancel out and the 2's cancel out, 1 over the square root of pi, integral dx e to the minus x squared. The integral e to the minus x squared is a famous integral. You've probably seen it. And you know it to be square root of pi. And that means we got it right. Our probability distribution is normalized. If you don't know how to do the integral, it's in Appendix A. It's actually a little bit fortuitous that we got exactly the right answer, because we made some approximations in which we ignored small corrections, which go to 0 as n goes to infinity. But actually, we did get the right answer. We were kind of lucky in that respect. Of course, if we use this distribution, which we now have verified is correctly normalized, obviously, if we compute the mean value of s, the integral ds of the probability distribution, we will get 0. Why is that obvious, by the way? Yeah?
Are you missing a factor of s?
Yeah, I guess I am. And in which case, it's not at all obvious. Thank you. It's obvious because the probability distribution is an even function. If we put in the factor of s, if we don't make a mistake, then we're integrating an odd function over a symmetric interval, and we get 0. So a more interesting calculation is to calculate the typical deviation from the mean. To get an idea what the fluctuations look like, we compute the expectation value of s squared. So now we're integrating from minus infinity to infinity ds s squared with our probability distribution of p of n and s. So now we're multiplying our Gaussian, which falls off like that, times a factor of s squared, which is 0 at the origin. The product is 0 at the origin. So this is s squared, and this is the probability distribution. So the product looks quadratic near the origin and then falls off like that. And so this is the typical fluctuation where the product is, actually it's the typical squared fluctuation, where the product is peaked. And to evaluate the expectation value, we have to do another integral. But we don't mind because it's kind of fun. Okay, so we need to do this integral. Let's write out again what p is. We have a 2 over pi to the n to the 1/2 to get the normalization right. Integral ds s squared e to the minus 2 s squared over n, integrated from minus infinity to infinity. So let's do our same change of variable again to simplify the argument of the exponential. So when we do that, for the expectation value of s squared, we have the 2 over pi n to the 1/2, and then we get a factor of n over 2 3 times now from the integration measure ds and from the s squared. So n over 2 to the 3/2. And then we're left with the integral dx of s squared e to the minus x squared. So we have to do that. But there's a nice trick for doing integrals like that, which is to consider this integral, which depends on a parameter alpha. which is the integral dx e to the minus alpha x squared. And now if we use our change of variable trick again, we can write this by writing alpha x squared as y squared as 1 over the square root of alpha integral dy e to the minus y squared. So that we know is square root of pi. So this is the square root of pi over alpha. How does that help us? Because we can differentiate with respect to alpha. If we want to get the integral dx of x squared e to the minus x squared, we notice that we can get that by differentiating I of alpha with respect to alpha. Differentiating with respect to alpha just brings down a minus x squared. I canceled that with the minus sign. And then we have to set alpha equal to 1 after we differentiate. So that's equal to minus dd alpha. And I of alpha, I told you, was the square root of pi over alpha, evaluated when alpha is equal to 1. And when I differentiate 1 over the square root of alpha, I get a minus 1/2. So the minus signs cancel, and it's the square root of pi over 2. So when we put together our factors for the expectation value of s squared, I have the 2 over pi n to the 1/2, like I said before, and the n over 2 to the 3/2, and the factor square root of pi over 2. So the pi's cancel, and I get 1 factor of n in the numerator, and I get 2 factors of 2 in the denominator, because this is 2 to the 3/2, and it's n over 4. So that means if I look at the expectation value in this Gaussian distribution of the square of the spin excess 2s, because now there's an extra factor of 4, it's n. And if I take the square root, it's n to the 1/2. So the typical fluctuation, the typical root mean square fluctuation of the spin excess from its mean value of 0, I'll call it delta 2s, typical root mean square deviation from mean, the mean in this case being 0, which is, by definition, the expectation value of 2s squared, square root thereof, that's the square root of n. So the fractional fluctuation is small. If I take what I call delta 2s and compare it to n, that's suppressed by 1 over the square root of n, and gets as small as you please as n gets large. So, from a certain point of view, the fluctuations are large, because if you want to play penny tossing with your friend and you win if there are more heads than tails, let's say you play for a penny a throw, and you and your friend are willing to flip the coin 10 to the 22 times, okay? Well, somebody's likely to win about $1 billion, right? About 10 to the 11. But on the other hand, compared to the total number of tosses, 10 to the 11 is peanuts. And so, in our model of a magnet, really what we should do to help out our experimentalist friend is we should compare the case of the fully polarized magnet for which the magnetization is essentially n times the magnetic moment of a single spin, with the case of random spins, where each spin independently decides whether to be up or down. And the magnetization in this case, if n is 10 to the 22, a little piece of magnet I could hold in my fingers like that, the magnetization could be up or could be down. And in terms of counting of spins, it's a big number compared to little m, the magnetic moment of a single spin. But it's about 10 to the minus 11 of the magnetization in the fully polarized case. And no experimentalist has the resolution to measure the magnetization of a bulk material to that accuracy. So 10 to the minus 11 typically goes by the name 0. Now, there could be fluctuations. You know, it could be if you play the game, if you are willing to toss 10 to the 22 coins over and over and over again, every once in a while, anything can happen, right? It's possible to toss a coin 10 to the 22 times and have it come up heads every time. Nobody can say it's impossible. It can happen. But suppose I'm interested in the chances that my experimentalist, let's say he's really, really good, okay? So he can measure a magnetization which is 10 to the minus 9 of the fully polarized case. Is he ever going to have a chance? If he has lots and lots of samples, will he finally be able to measure a non-zero magnetization? Well, we could ask, how likely is a spin excess of 10 to the 12? That doesn't go all the way to what he can measure. That corresponds to a fraction of fully polarized, which is 10 to the minus 10. So it's a large fluctuation compared to the typical one, 10 to the minus 11. It's a factor of 10 bigger. Doesn't sound like a big deal. A factor of 10 bigger ought to happen once in a while. But in fact, if n is 10 to the 22 and 2s is 10 to the 12, then we're talking about 2s over n of 10 to the minus 10. And so the Gaussian factor, the e to the minus 2s squared over n, is going to be something like e to the minus 50, which is 10 to the minus 21. Okay? So he's going to have to measure a lot of samples, right? 1,000 billion samples before he's going to find a magnet in which the magnetization is 10 to the minus 10 instead of the typical value of 10 to the minus 11. Essentially never. Okay? He's good and he's patient, but he's not going to measure 1,000 billion times, so it's always 0. Okay? The large fluctuations are extremely rare. And that's the big lesson of statistical mechanics, and that's why it works, and that's why we're going to apply it for the rest of the term. It's going to be a lot of fun. You know, it's all about fun, and this is a fun course. I put a comment form on the website. If you want to give me feedback, you thought the lecture stank, or even if you liked it, or you thought it was too fast or too slow, or something like that, feel free to comment and I may or may not pay any attention, but I actually appreciate the feedback. Yeah. Well, yeah, I put that on the website, and I think I just copied it from last year. So what was it last year? I think I forgot.
It says Thursday.
What was it?
It says Thursday on the website.
Is that wrong?
Yeah, Thursday.
Okay, so it says Thursday on my website, you mean? Okay, well, that's the ultimate authority. So it's Thursday.